Welcome, everyone. For today's prep, we're going to look at an example for how we actually use this limit definition of derivative. So first, let's read through the definition here. So f prime of x, that's what we call our derivative, and it's equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And we'll go through this in class a little bit more, but you want to think of this fraction here as giving us, this is the slope of our secant line. And then we're watching what happens as that secant line kind of moves closer to match up with our tangent line. But in any case, this is our limit definition of derivative. So let's see this thing in action. And we're going to start, we're just going to do example 1 here and see how this works. So we're going to find the derivative, in this case, of a polynomial. And our polynomial here, the function we're going to differentiate is x squared plus 2x plus 2. So we're going to find the derivative of this function. So when we're doing this, you can think of this almost as a kind of a step-by-step process. So the thing usually it's kind of helpful to do first before you do anything else. You don't necessarily have to start with this, but it's usually helpful. Figure out what f of x plus h is. And this is kind of the trickiest part a lot of times, is just doing this evaluation. It kind of looks a little strange. So we spend some time with this. And then we calculate what's called the difference quotient. So the difference quotient is the fraction. Then we simplify that difference quotient. So we try to simplify the fraction down as much as we can. And then finally, we do our limit as h goes to 0. All right, so let's see all these steps in action. So we've got our function f of x. And when we go to calculate f of x plus h, what we do is in our original function here, wherever we see an x, all we're going to do is replace it with parentheses x plus h. So that's the first step. First thing we probably want to try. So I see an x here. I'm just going to replace that with parentheses x plus h. I see an x here. I'm going to replace that with parentheses x plus h. We got an x here. You guessed it. Replace with parentheses x plus h. And the parentheses are important because this 2, well, when we go to simplify it, this 2 is going to distribute. And same thing here, this x plus h, that whole thing is going to get squared. So we're going to have to multiply that out. All right, so once we get this written out, now we actually want to kind of multiply things through. So let's see what we get when we multiply this x plus h squared out. And if you need to, it definitely doesn't hurt. Maybe do this off to the side. So that x plus h squared, we could think of that as x plus h times x plus h. And then when we go to multiply, we use FOIL. So the first we multiply, and when we do that, we get x squared. Then we multiply the x with that h in the other term, so we get a copy of xh. Then once we've kind of multiplied x, that first piece, into everything in the second parentheses there, then we go on to the second piece here. And we're going to take h and just multiply it. So when we do the h and x, we multiply those. We get another copy of x times h. And then finally, we multiply the h's together. So we get an h squared. So it definitely doesn't hurt, if you want, when you're doing this, to show this as part of your work. You know, maybe do it off to the side. All right, so if we kind of simplify that down then, we have our x squared, and we have 2 copies of xh that are getting added. So we'll have 2xh, and then we've got our h squared. And so this is that multiplied out. Now over here, we can multiply out the 2, so we can distribute the 2. So we get 2x plus 2h. And then finally, we have our plus 2 at the end. And sometimes there's, if we multiply all this stuff out and we multiply all this stuff out, you just want to see if there's any terms that you can combine. But in this case, we can't. So none of these terms we can combine in any other way. So this is about as simplified as we're going to get this. All right. So once we have f of x plus h figured out and kind of multiplied out and everything, then we're going to go on to our difference quotient. So f of x plus h minus f of x all over h. So that fraction in our limit definition. We call this the difference quotient. All right, so how do we do this? Well, we'll get a big set of parentheses. And from this big set of parentheses, the first one here, we're going to fill in our f of x plus h. That's what we just figured out. So our f of x plus h here we found to be x squared plus 2xh plus h squared plus 2x, didn't make it big enough, plus 2h plus 2. All right, so that's our f of x plus h. Then we're going to subtract, and then we have another set of parentheses here. Make sure I make those big enough. And in that second set, this is where we're just going to fill in just the original function. So just the original function that we're trying to differentiate here. So our x squared plus 2x plus 2. So that's what we're going to fill in this second set of parentheses right over here. All right, so we've got our f of x plus h minus f of x, and then we're going to divide this whole thing by h. Whew, okay, so we've got all this stuff, and we have our difference quotient all figured out now. So this is our difference quotient. So let's see how we're doing. Calculate the difference quotient. We did. Well, we figured out f of x plus h first. Now we want to simplify that fraction, that difference quotient. And this is kind of the fun part. Some of you might argue with that, but this is the fun part because a lot of canceling happens here. And you want to start by looking at all the terms here, because usually when we're doing these, all these terms end up getting canceled off from the original f of x. So when we do the f of x plus h, there's kind of some additional stuff in there that cancels off all this extra, or cancels off the original f of x part. All right, so when we're doing this, let's start with this term here. So we have an x squared, and then we want to look over here to see if there's any x squareds. And we see one right here. We've got an x squared. So because we're subtracting, this x squared here is going to cancel off that x squared. Again, we're subtracting here. That's why they get canceled. Okay. Now we go to the next term. It's a 2x. So again, scan through this first piece, look to see if there's any 2x's. And boom, we got one right there. So 2x cancels the 2x. And then we have a 2 all by itself. Again, scan through. We've got a copy of 2 over here. And because we're subtracting, those cancel. All right, so once we do all that cancellation by subtraction there, then we want to just kind of write down, well, what do we have left? So nothing happened to this one, nothing happened to this one, and nothing happened to this one. So let's kind of rewrite those. So we've got our 2xh plus h squared plus 2h all over h. And now the next step to simplify this down is to try to factor the numerator. We ultimately want to get this h canceled off. So if we do that canceling, you can think of this a few ways. You can think of this as, since we're dividing this whole thing by h, what we're really doing is we're dividing each of these individual terms by h and then adding the results. Or you could think of it as this term has an h in it, this has two h's, this has an h in it, so we could factor out a copy of h from all the terms in the top. And now we have a factor of h on the top, we have a factor of h on the bottom, and we can cancel those out with a little provision here, provided our h value doesn't equal 0. So as long as h doesn't equal 0, canceling this out gives us an equal formula for our function, our difference quotient. So then all we have left is 2x plus h plus 2. So, we started off with this big complicated difference quotient, and we did some subtraction, we did some factoring, and then we get it down to this point. And as soon as we kind of cancel this h off, now we're ready for our last step. And our last step is to calculate the limit of this simplified version of our difference quotient. And notice that we're okay because we're doing the limit as h is getting close to 0, but it's not quite 0. So h doesn't equal 0. Okay, so we're going to use this simplified version of our difference quotient. So the simplified version here is just that 2x plus h plus 2. And now we use our limit technique of direct evaluation. And the tricky thing here is a lot of times when we're doing this, we should have x's and h's in our expression. So we have some x's, we have some h's. So when we do direct evaluation, we're looking at the limit sign here to tell us which variable we should be considering. So in this case, h is the thing that's getting close to 0. So our direct evaluation is we're going to plug h equals 0 in. So our answer here should ultimately still have some x's. So if we do this, if we do the direct evaluation, now no more limit sign, and we're going to have the 2x. We're going to plug 0 in for the h that we have, so we'll have plus 0 and then plus 2, and then if we simplify, we end up with 2x plus 2, and that is our derivative. So these are kind of fun problems, so we'll be trying a few more in class, so for some additional practice. So we'll see you then. Bye-bye.